Awesome. All right. Well, let's get started today. Again, thanks so much for joining, and we're really excited about today's webinar. Uh, we are going to take a deep dive into SLS 3D printing and review our new high-performance materials available through this partnership with Stratasys Direct Manufacturing. I'm super excited, and we've been practicing this week. It's just an awesome lineup of SLS additive manufacturing experts. Combined, we have over 30 years experience in the field of additive manufacturing. And it's really exciting because these co-hosts, they're from Stratasys Direct Manufacturing themselves. And I'm with Xometry, and Stratasys Direct Manufacturing is the OEM or service end of Stratasys, which you may know from some of their machines like Fortis FDM, for example. But yeah, let's go ahead and get started. First off, I'd like to introduce myself. My name is Greg Paulsen, and I'm the Director of Application Engineering at Xometry. I've worn many hats, being a buyer, a designer, a supplier of additive manufactured parts, as well as other projects. I've had hands-on experience with SLS, actually was introduced in 2007 to the technology and ran machines for many years through my previous career, as well as at Xometry here. I love talking shop, DFM, talking applications, and helping customers choose the best materials and processes based off their project to make it successful. And joined today, we have some amazing co-hosts. So let me introduce these experts. And again, they're from Stratasys Direct Manufacturing. So first off, I'm going to introduce Louis Sims. Pause for applause. He asked for the pause there. Anyways, hi Louis. Louis Sims is a solution manager at Stratasys Direct. His mission is to help the manufacturing community leverage the best of additive and conventional manufacturing services that Stratasys offers and solve problems to serve their ever-expanding breadth of manufacturing opportunities. He holds deep industry expertise in powder bed fusion and is passionate about production manufacturing when it comes to additive. Along with Louis, we also have Kevin Sheehy. Hooray! Yeah. And with Kevin's a manufacturing engineer at Stratasys Direct. In his role, he supports the additive polymer department, focusing on powder bed fusion through selective laser sintering, multi-jet fusion, selective absorption fusion, which is new to me, SAF. And some of his projects include material development, manufacturing process control creation, and new product introduction. Kevin has a BS and MSc in mechanical engineering out of the University of Texas of Austin, which actually has a terrific additive background in history there. So we're going to talk a lot about selective laser sintering, additive manufacturing, and there's a lot to cover today. Some stuff to note before we begin is that we love answering questions. There is a Q&A box in the GoToWebinar program. You can select. Please feel free to write questions anytime during this webinar. We're going to try to keep time at the end to cover as much as we can. Also stick around for the end to get a special promotion for attending this webinar to help get some discounts on SLS parts you can purchase through Xometry. So today we're going to talk about SLS, selective laser sintering. First, we're going to answer, what is it? What is SLS? We're then going to talk about why is SLS, so these benefits that you have with this particular technology. And then we're going to go down into the materials that we have immediately available through Xometry and our partnership with Stratasys that includes these nylon variants and some of these high performance materials, and a little bit of a summary of a material landscape when it comes to the industry for laser sintering in general. I also have some tidbits and some tips for designing parts for getting great parts out of the SLS process, as well as some post-processing finishes that you do. And again, anytime along the way, please feel free to submit your questions because you have some awesome experts. And part of the fun of doing these webinars, I'll guiltily admit, is just chatting with the experts beforehand, really working through. And honestly, any question you could ask about this process, we have the resources here to answer it. So I've mentioned this. We have a partnership with Stratasys Direct Manufacturing. So Xometry is a manufacturing marketplace. We're able to access expertise from all different fields, and Stratasys Direct has about 30 years of applied experience in these various technologies. With our recent partnership we've been able to add 4 uniquely new materials to Xometry's lineup for selective laser sintering. And I hope that's just the beginning, because there's a lot out there. And it's allowed us to instantly quote these and gives you more choices when you're choosing different materials for your manufacturing project. And Louis, I'm not sure if you wanted to chime in as well on this.
Yeah, absolutely. Thanks, Greg. Xometry has done an excellent job of really democratizing access to 3D printing with its incredible online marketplace. And Stratasys Direct is so excited to partner with you guys on bringing our SLS expertise, our 30 years of experience, and probably one of the largest SLS capacities in North America to you guys. So thank you for partnering with us, and we're excited to talk about these high performance materials with you guys.
No, it's awesome. So, like I said, there's a lot to talk about. Let's just go ahead and get started. First off, Xometry, SLS is one of these processes. We actually offer 7 additive manufacturing options, as well as traditional manufacturing like machining, injection molding, and sheet metal and urethane casting. But these manufacturing is an umbrella. It is a bunch of different technologies that do something a little bit different than traditional. We're not taking a larger chunk of stuff and cutting it down to create a shape. We're taking something that's lesser, like a filament or a liquid resin or a powder, and fusing, bonding, and mechanically attaching that together, driven by CAD, to create that part. We have a few different ways of making parts, and these are these different technology categories. For example, PolyJet, SLA, and Carbon DLS. These all use a liquid resin that is cured with a UV light in some way, shape, or form to build a 3-dimensional shape. You get some great surface finishes for it. They are axe-like polymers, so they tend to be axe-like ABS, but it's actually a photopolymer base to it. Carbon DLS has the extra advantage of a post-thermal cure to give it more of a urethane-like property for longer durability and use than PolyJet or SLA. We also have fused deposition modeling. So FDM, you may think about like a desktop 3D printer where you have a filament, and from that reel, it's melting that filament down, zigzagging back and forth, and building your part from the bottom to the top. We have the industrial version of those. So they're actually Stratasys products, the Stratasys Fortis FDM line. We run all the materials under that Fortis line, and that includes materials like high performance Ultem, polycarbonate, ABS, ASA, and you can build parts up to 36 inches in this. The benefit there is that it is plastic. It's real thermoplastic. So again, it's a great option, especially when you're making larger, broad parts and for manufacturing. We can print in metals. Direct metal laser sintering is actually one of the 3 powder bed fusion platforms that we have. In this case, think steels, aluminum alloys, nickel alloys, titanium. And DMLS, it will use a laser to fuse it together and kind of build a part from the bottom to the top for a nice performance metal part. And then these plastic powder bed processes, so SLS, selective laser sintering, and HP multi-jet fusion. Honestly, a lot of times you have to twist my arm and tell me why you're not choosing these. And I think the theme of today is why aren't you choosing SLS? Is going to be what it's all about. But they're extremely versatile, tend to have high performance but low cost parts that could be built in bulk. And again, today, our hero is selective laser sintering. So we're going to start with what is SLS? And Kevin, I'm going to ask you, what is SLS?
Thanks, Greg. So selective laser sintering, or SLS, if you didn't catch from the previous slide, us in additive, we love all of our acronyms. It stands for selective laser sintering. So it's a laser powder bed fusion process that is actually creating, has the ability to create parts in bulk. And it's doing this in an inert heated chamber. You can kind of see this big, I think Greg calls it the big white refrigerator right there. This is actually one of the machines. So that flash of light is where the process is actually taking place, and there's nitrogen being pumped in there, so there's no oxygen in that chamber. This has been tested in many different applications in industry. One of the reasons behind that is we can make real thermoplastic parts in high throughput. It's also been around for quite a while. This is one of the earlier technologies to come out of 3D printing. It was invented actually in the 80s at the University of Texas. So got to do a hook'em for that. And so jumping into why SLS? Why would you use this technology? The first huge value proposition is these are real performance polymers. You are getting a true thermoplastic that can work in a wide variety of applications, whether you're putting it through high stress, temperatures. These are going to be able to stand that test of time. One of the things that a lot of people have this misidea about is that it's these loosely bound particles that are barely necked together. That's probably because the name of selective laser sintering, but this is not a sintering process. These are a full melt. It is a liquid during this process. And so if you cut like through that body of the car on the slide, it would look like any old injection molded part. It's a fully dense plastic that's being able to be created from this process. So another huge benefit is there are no supports that are required. While this process is building up layer by layer, it is being supported, your parts are being supported by the unsintered powder. So you can take a look at this part. This was a single piece printed in the machine. All that we would have to do after it was printed is take it out and do a little bead blasting in order to get your final part. It's different in a lot of the other additive technologies that you're not worrying about, man, do I have to have this overdraft angle? Do I have to have this connected down to the base plate? You can design your part with purpose and you don't have to worry about, how is it being oriented in this 3D space and how's it touching?
Yeah, actually, I would have, if I gave this, for example, an FDM, I would have one of our technicians yelling at me about how the machines hate me because of the retraction that would take to actually make this part. And then it would probably break instantly because you have anisotropic properties that are more extreme in that process. Just a fun fact, though, this is actually one of the part that has been around at Xometry for about 7 years and been tossed around like a toss ball. And the nerve bundles kind of act like their own spring, going back to the thermoplastic. So it's survived a beating, and it's again, given the complexity of it, it's pretty amazing.
So one of the other huge benefits of SLS is that because there is no supports, you're actually able to build in a 3D space. So you can batch together a ton of, for example, in this slide, this same part. If you're going into production and wanting to make 100, 200, 300 of these, you can put them all together in one giant build. Or if you're making a assembly, or you just have a bunch of different parts that you're doing for production, you can place them in this 3D space, and there's no real negatives of having, on one build you had one geometry in there, and then the next build you have the next. The process doesn't particularly care what's next to it.
Yeah. And to that note, I think I did an audit just to kind of get some real numbers behind this. Taking an example build from the other day, we had 120 unique parts built in one build, which is about a 20, 30 hour process. And that was across 20 unique orders. Again, this is a process that just favors the many.
So here's actually how does SLS work. This is a video of the printing process. So the first thing that happens, you can see this recoder goes across the print bed. And so what it's doing there is it's putting a fine layer of this powdered plastic across the build chamber. Each of these layers is 100 microns for this process. And so in between, while it rolls across, there's powder in that slot that's being laid down at an even layer. And then you see that flash of light. So what that is it's an IR heater that's bringing the powder right up to below its melting temperature. So it's right around 180 C or so. Once that happens, it's kind of hard to see in this video, but the laser is shining down from above and melting that plastic to create your parts. So the laser is, etching across the entire cross section of that part, and then it repeats and goes over, drops 100 microns. That recoater adds more powder, and this continues for thousands and thousands of layers. So then the parts cool, and you take them out of the printer, and we call that mix of unsintered powder and parts the part cake, or the cake. And then you go through kind of an archaeological dig to get your parts out. So you're digging through all that unsintered powder, pulling out your parts, brushing them off and bead blasting them, and that's how you go through the entire process.
Yeah, and these are a couple examples of what that build looks like. So as Kevin was noting, you're using a laser and you're bonding those materials together with that laser, as well as that layer underneath to give you that Z dimension. And you don't see the movement because it's so subtle, as you mentioned, that 100 micron, but there's essentially a build chamber with a platform lowering underneath as it's building, and you have your parts. So in this case, these two examples are examples of a set of parts, like an assembly, that are ordered in bulk. As I mentioned, it's not always that case. A lot of times it's a high mix, or there's a bulk order mixed in with some individual onesie, twosies, 12sies out of there. But it kind of shows you what you can do when you don't need support structures. I'm not just bonded to a build, flat build area, and I just look, two-dimensional top and bottom. I can actually nest parts together, bring them about 2 millimeters to 4 millimeters apart from each other, and move them in a way that they configure. We also use software to nest these parts to optimize that build. One of the things you want to do is you want to optimize for the build height that you're doing, and distribute actually the scan time per layer, so the amount of work the laser is doing each layer, and try to keep that as even as possible to get even heat throughout the parts and kind of a more consistent quality throughout there. But yeah, you can see just high complexity, throw it all in, and you could build these parts 20 to 30 hours later, let it cool for about 12 hours, and then you could break out the parts. So we have materials. Xometry's been offering SLS for a while. We have our own internal facility with selective laser sintering platforms as well. Historically, we've been offering the unbolted material. So Nylon 12, which is still extremely commoditized, extremely available, and Nylon 12 glass fill variant, and we'll go into that a little bit deeper. But with this partnership with Stratasys Direct Manufacturing, we now have Nylon 11 EX. We have Nylon aluminum filled, Nylon mineral filled, and Nylon carbon filled. So different high performance polymers. A lot of these are preferred when you go from that prototyping low volume to production, and we're going to go deeper into these materials. So let's start with those commodities. And in this case, I'm considering commodities the unfilled materials here. I'd like to clarify first about nylon. Why did I just mention nylon 6 times to you? So nylon is the most common polymer that you'll find in powder bed fusion processes, not just SLS, but anything that's using some sort of heat to fuse together powder. One of the biggest reasons why, especially these variations of PA12 and PA11, which has to do with essentially a monomer chain on the chemical composition of it, you literally count it, and that's 11, it's PA11, count it 12, it's PA12. But one of the reasons why these are used so commonly is because they have a really narrow melt transition. So I have this heated thermal chamber. I have this powder across it, and I want my laser to just hit it and nudge it into a melt state. And then I want it to recrystallize as soon as possible. Why do I want that to happen? Because it turns out I like my features on my part. If you get nice, clean features when you're printing parts in SLS, because that melt transition can quickly go from a liquid state to a solid state without essentially running like a puddle. So it's the opposite of what I want in injection molding nylon, for example, where I may use a nylon 6 resin that has a fantastic flowability, can get small feature details, and really fill up all the nooks and crannies of a fine detailed design. But that material, when you're using it for sintering, is actually more temperamental because it can get blurry. It actually can kind of create a little melt pool versus just a nice a nice, clean, discrete melt point when you're doing that. So that's why you see these materials so often. But going to into the details there, what does one monomer chain do to these parts? And I think, Kevin, again, I'll give you the mic here, but let's just talk about nylon 12 versus nylon 11. You know, what's common and what's different about them?
Yeah, so nylon 12 and nylon 11 are going to be by far the bulk of everything that you're seeing in SLS, like Greg said. They are very similar materials. You know, the carbon backbone changing between 12 and 11. But one of the quick and easy ways to distinguish them is where they're actually being derived from. So nylon 12 is a petroleum derivative, and so the big difference and one of the benefits of nylon 11 is that it's coming from a renewable source. It's coming from a bio castor bean, so it's being grown, this bean, and then distilled into this oil, and then that's what's actually creating that polymer. You know, it is Earth Day, so happy Earth Day,
Yeah,
everyone.
happy
This
Earth
is,
Day.
you know, something to talk about. And one of the other huge benefits of just the SLS process is that you actually get high reusability out of both of these materials. So like we were talking about, that you have all your unsintered powder that's surrounding your parts, you actually can take a large portion of that used powder and blend it in with some new virgin powder, and that's going to actually be what is printing your parts. So you get the benefit for both of them is they are highly reusable, and then that added benefit of nylon 11 is that it's coming from a biosource. And then as far as the chemical resistance, both have great chemical resistance. You can put these materials in a lot of different fluids and oils, and they're going to survive. Nylon 11 does have slightly more, but they're both great in that regard. And then one of the other ways to really differentiate these two materials is the elongation and the impact resistance that come along with nylon 11 compared to nylon 12. When we look at a stress strain curve on these sort of materials, perfect, the elongation on the nylon 11 is over double of what you're seeing on these nylon 12s. Nylon 12s tend to have, especially in the z-axis, which is, when I say that, I mean it's building upwards, so the layer to layer adhesion, it is closer to a brittle break, versus this nylon 11 is a much more ductile, and it has this elasticity and ductility that is great in a lot of high requirement, high stress applications for your laser sintered parts.
And
Yeah.
I got a piece here. I don't know if you guys see the camera. So this is the nylon 11 EX. And I know, Louis, you were talking about EX. You have this combination of these great properties and actually great detail out of this. But I mean, the flexibility is fantastic. And one of the ways I've used this in the past, and actually I used to run a lot of nylon 11 when I did defense electromechanical systems, and these are like wearable things and stuff that that could accidentally, fall on the floor, get rolled over with, or get stuck into a door when you're closing it. And nylon has this amazing ability to take a hit and then flex back and just go back into shape. And with nylon 11, it's even more ductile there, and it actually has some advantages over making something out of metal, right? So like you could bump metal and it could dent, and then you have a permanent dent structure. When you work with something that's ductile, it reforms in a lot of cases.
Yeah, absolutely. I have a great example for that. We have an aerospace customer who transitioned a metal, 18-piece assembly to one contiguous nylon 11 component solely for that reason. They avoided over $100,000 in rework just because as they were installing those components, they were breaking them, they were damaging other areas of the aircraft while trying to install it. So they were able to, improve installation. The part was still as robust as they needed it to be, and then obviously you save a ton of time and money and reduced assembly costs as well. I would say certainly if you have experience with nylon 12, then you're looking for something that gives you a very similar part, but with a little bit better maybe ruggedness or high performance in terms of that impact resistance or that higher elongation. Definitely try out the EX variant. We offer both kind of a standard nylon 11, and then what we're here to talk about today is the EX variant, which is going to give you everything you want from the nylon 11, but with much crisper feature detail and resolution. So
yeah, that's what we have. So like the actual brand of it is Real Sand Invent Natural. It's through Arkema, which is, by the way, where I got this this awesome data from. And yeah, it's just a fantastic material. And as Lewis mentioned, like really good when you're moving the step of the production where you want something that has, you know, the reliabilities, maybe a little bit extra performance, extra little ruggedness to it.
yeah, absolutely. It's our most utilized production material, and for a good reason. So
Absolutely. So the other category, so again, like when I say commodity, by the way, these are still really good materials. And I have to mention, like one of the fun parts of my job is I break parts all the time, and I have a so this is a SLS Nylon 12, and I went through 10 minutes of essentially a durability test, where essentially a constant drop test, and it lost some features, okay, but it survived. But when you compare that to, you know, an SLA part after 16 seconds of the same test that essentially lost most of it before I stopped it, and it was like, oh gosh, that's just going to be all pieces. Carbon DLS epoxy, you know, after 7 minutes. Polycarbonate, you know, it just you know, holes through it. This is the commodity material, and this is the cheap one. Like this is the regular one. So when you look at the less, it really just reinvents the standard for what to expect out of performance. And I'm saying that because I'm about to phrase this into high performance. So we just said like these commodities are tough. Let's talk about this. And Kevin, again, I'll give you the mic on here. And by the way, I see some questions coming in. I'm looking forward to addressing these. So please keep them coming. This is awesome. It's all glass fill.
Yeah, so when we talk about these high performances, what the big difference is that there's some sort of additive or filler going into these materials. So it still is the same base, you know, for this one, it's a nylon 12, and then we're adding in a glass to this material in order to get some property that you're not able to get with just the base polymer. So for example, this glass filled material is great for dimensional stability. Glass is amorphous, so it doesn't shrink like these polymers do, which are, you know, 3 to 4% or so. The glass doesn't. So if we're getting, especially into these really large parts where we can get, you know, 23, 24 inches of a part in some of these laser sintered machines, if we're getting that large, a lot of these standard materials, you start to see some unpredictable, uneven shrinkage, and makes it really difficult to keep the stability of your part. So we add this glass in, and now you're able to print a part, and it actually turns out like how you designed it and how you want it. It's much closer to the final CAD. And then some of the other benefits of the glass is rigid. You're going to have a much more dense and rigid material coming out because of this additional glass into the material. It does great for, you know, prototypes, jigs and fixtures, and if you really want anything big, I would suggest going with this glass.
Yeah, and something you'll find on Xometry's instant quoting engine is when you upload your 3D file, if you do have a larger file, I think the threshold is somewhere around like 15 or 16 inches, it'll go to a RFQ state where we need an expert review if you're choosing an unfilled nylon like a nylon 12 or nylon 11. And to Kevin's point, and I'll go into this on some design tips later, long, broad parts tend to have some flex or warp or some unpredictable tolerances based on the design intent. Some designs are more stable than others. When you add a fill to that component, you have much more stable designs. And also we have, you know, larger platforms that are typically running materials like glass fill. So you'll be able to instant quote larger parts and even see the economy of scale be better on those larger parts versus an unfilled material in a glass fill variant, for example. And actually, I'm going to answer a question because it's a good segue because we talk about large and small in this. A standard SLS machine, like the EOS P300 series that we have at Xometry, is going to be about 13 by 13 by 23 inches of space. And then there's essentially a double size of that. So like imagine two of those spaces beside each other. And that's those are usually the platforms for these larger machines. If it's EOS, it's going to be like a P700 series. Just know that it has a dual laser to it. So sometimes if you have a really long part that's really big, like say I'm making an entire dashboard for a boat or something, there may be a seam or something that's a little bit, you'll see where the laser actually kind of meets up right in the middle of that. Just a note there. But we may use the larger platforms too for production to just fill it up with parts if lead time's not a giant issue. Moving on though, so we have glass fill. Now we have aluminum fill. Like this is actually one of the new Stratasys direct materials for our partnership. So let's talk about that.
Yeah, so for this one, as you can see on that first bullet point, these make beautiful parts. These are one of the real shining stars as far as if you want an aesthetic part, but also the ability to have the applications that come along with a nylon 12. So it has kind of this gray metallic appearance because of the aluminum fill. And so you almost get like a sparkle from these aluminum filled parts, and the picture really doesn't do it great. I mean, it's
I'll try to get a
yeah,
sparkle shine here.
yeah, as
Even
the
the video
light
doesn't
shines
justice.
off it, it kind of,
Yeah.
it's great for concept models, any metal look-alike part. So if you were trying to just do a looks like prototype and you don't want to actually go and machine, a piece out, or you don't want to have to go through all that additional trouble, and you're just trying to see, how does this look? And you want to make sure it still has that metallic look. This is a great one for you, but I don't want to take away and say it's only beautiful, because it does have that added stability from that aluminum fill.
Yeah, it is just great for those for concept models, and oftentimes I do a coin toss if you want to use aluminum fill or glass fill. Properties are similar enough that like other than like elongation, but a lot of times you're using these rigid stable parts not because you don't want them to elongate, or you're not going to put some sort of pull tension on it. So yeah, it is a coin toss as well.
Yeah, absolutely. It's got a fairly high fill rate for the aluminum, around 50% by weight. And I know Greg and Kevin will fight me on this, but if fine feature detail and aesthetics are important to you for any particular application or prototyping that you're doing, I think this is your material. You can see there through some of those cylindrical features that it resolves very, very well.
Yeah, it's really clean, but I'll see you in 2 slides, Lewis, on that, and we'll compare notes here. Just let me get out of that. Excuse me, I just pressed escape. All right.
All
There we
right,
go.
so
Yeah.
our next one that we're talking about is a mineral filled nylon 12, or HST, high strength, high temp. The name is exactly what you'd expect out of this material. If you want to have a material that is being pushed to the limits as far as its application, this is a great option for you. It has one of the highest HDTs. You're going to be able to put this in much higher applications as far as, if it's going to be exposed to heat and it's also under pressure. This really does hold up in a lot of those sort of production end use part applications. It's also RF transparent, so if you're doing something like a drone body and you need to make sure that you can still communicate with it, you can get those radio frequencies through it. So a lot of great end use sort of enclosures, structural elements, those production applications are where HST really shines.
Yeah, and I know we were talking about this a little bit when you work in electronics enclosures. Something that I found in a previous life was that using a rigid SLS material like HST was really good for structurally holding PCB inside a assembly or enclosure that may have a higher cosmetic need. So a lot of times you may do a mold or urethane cast of an enclosure, and then you actually have you're able to use this really fun freeform design that you have with SLS and junction one PCB or many together in a way that it fits within that enclosure. What that also has an added benefit of doing is when you change your rev in additive production, it is so seamless because you just put in the new file and you run the print. Where it's not like changing a rev on a tooled product, for example, where you have to update the tool or even fully replace that tool or change your setups if it's a machine product. So if you have a PCB rev or something goes out of date and you need to change a little bit of the design or move a hole, no problem. Update the revision of that component that's kind of in the hidden side of your assembly, and you just print it for the next run. It's awesome. So, Louis, I think CF it's my favorite material cosmetically when it comes to SLS in general. And I'm hoping to get a 2/3 vote on this. But yeah, Kevin, tell us a little bit about
I'm
carbon fiber
sorry,
nylon.
Louis. This is my favorite material by far. You get great detail reproduction because it is a nylon 12. You can see on the bottom of this slide right here where you see that 12 CF, how crisp that is. And when you're looking on those curved surfaces of that dome, they're really beautiful parts. But these aren't just a beautiful thing. What's great about these is it does have the carbon fiber as part of them. So these are really lighter weight, but incredibly stiff parts. These are going to be our highest stiffness of any of the SLS materials. It also, because of that carbon fiber, is great in temperature. So just like the mineral fill parts, this is going to be a really high HDT, and you're going to be able to push it to the limits, and that carbon fiber really holds its stiffness. One of the things to note about this material is you're going to get orthotropic properties. So what does that mean? That X versus Y versus Z, if you were looking down at the printer, you're going to have different properties through each of those orientations. And so while it's printing, how we showed the recoder moving back and forth, and that powder stack is being laid down through each layer, the carbon fibers tend to orient along with the direction of the recoder. So what does that mean? Your X is going to have most of the fibers lying in that direction, and so they're going to see the highest mechanical performance. Y has some, not as much, and then Z has the least, because if you're thinking about these fibers, you'd have to somehow roll them and then them stick up through the print.
Yeah.
So that's just not really going to have quite as much. But just something to kind of think about, and it's just like any other carbon fiber layup, like the direction of the fibers makes a difference.
And I think because of some of the applications, Lisa, I've had experience with CF, where I've used this to build plenums and things that are going to be driving air or something where there's going to be something moving through. So you want some of that dissipation so you don't get a static buildup. I tend to see a lot of organic curvatures, particularly with this material. And maybe you may have different experiences, but like I said, talking about the cosmetics for a second, like the way that curvature really shows this, and this is an as printed part. This is non post process, tends to just have really clean look to it. And to your point about that orthotropic property, even from the electrical conductivity, sometimes you could get an ohm meter and stick a pin on one side and get a readout on the other. But if you start dragging up and down, you'll see that you get hits or misses, and it has to do with those little carbon links, like does it exist there or not. So it does change a little bit, but you still have, this is still the highest performance SLS material that we have. And I want to summarize this. You do not need to read this. This is what's important is this left-hand column, which is this is a graph actually from Xometry's Ultimate Guide to 3D Printing under our Resources tab. And it's talking about the kind of a material landscape. I like to think of it more as a Rosetta Stone because there are different materials out there that have equivalencies, or are at least in the same family. So we did talk about these unfilled materials: glass filled, aluminum filled, carbon filled, and depending on the the manufacturer, material manufacturer, these are some of the major ones that you have, you may know some different terms. That's why you may see that EX or HST, or you may hear like alumide. Sometimes it's like the term used for aluminum filled because it's a brand through EOS. But just understand these are, alumide and PA605A are both 50% by weight aluminum filled nylon 12s. So this is handy. If you want to rewatch this webinar, press pause here, or you can actually get this exact graph under Xometry's resources under our ultimate guide if you go down to our processes for SLS. The one exciting thing is there's some neat stuff down here. And again, I hope this is some expansions in the future. Some of these require completely different platforms, like to hold temperature for things like peak and peck. But SLS, just like a lot of these other additive processes, are having kind of a revolution when it comes to what materials are available. There's one thing about the materials being developed, and there's the other side where you could actually buy those materials and get them, made somewhere. So just understand that too. So I'm going to move into tips for making great SLS parts, because we've talked a lot about this. We talked a lot about materials, the properties, but what do you get? I pressed buy today, for some small parts, you're talking like, you could buy a part for like $10 in SLS. A lot of these parts are sub $100. Larger parts can be more. As built, the finish is a matte sugar cube-like surface. So when you feel it, you feel some of that grain. As Kevin mentioned earlier, if I took a bandsaw through it, it's going to be fully sintered on the outside. But about that outer, 20 thou or quarter millimeter of any sintered part throughout different processes tends to be kind of the weird zone, like the zone where you tend to see a little bit of a thermal change that will create a rough surface similar to the material that was used to build. You see that in metal printed parts, you see that in multi-jet fusion, you see that in SLS. Understand that all additive manufacturing is making a near net shape. The general dimensions for SLS is plus or minus 0.005 of an inch. And then I think of over like 4 or 5 inches, it's plus or minus 0.002 of an inch, or whichever's greater per inch. But parts that are about the size of my fist or smaller tend to be extremely dimensionally stable to your CAD. The larger you get, it's geometry dependent. If you have like large cantilever features or a thick part next to a thin part, there may be some deviations they'll talk about. The detail resolution's good. It comes out really well. Smaller details tend to get rounded out. So again, if that 0.5 millimeter range is really and below is really a struggle for this because of a laser, the actual lasers that are used in the material itself. And something else to note is that holes in this process. So when you design a hole, when it prints, because it's a thermal process, the holes will shrink slightly. Xometry is a standard of our service. We are going to actually measure the digital CAD of that hole and drill it out if it's a standard drilled size and round. If you have a hexagon or something like that, we have some design tips like putting a offset of that face by about 4 or 6 thou to compensate for that. So some great examples. I actually like to choose this. This is actually from a recent case study that Xometry had. But this is a as-built SLS nylon 12 prototype part for a valve splitter. What I like about this part that really show off the details and almost like a challenge part is you can see that this part here was built vertical. You can see some layering, but it's not as direct as what you would see on a fused deposition modeling part where you see very discrete layers, and especially a lot of changes in resolution, whether it features vertically built or horizontally built or at an angle. So SLS is very good at that free form design. The text resolution on this is like I said, good. You have a little bit of roundness, but I could read everything here. And parts that are even built at different angles are still able to be resolved very well. And in fact, something interesting about SLS is that a lot of times if I have text or features, I try to angle it. I actually try to build it at a diagonal or a vertical versus a top and bottom, because you tend to have better detail resolution overall.
Yeah, I really like this example of this part for what SLS is great for. So you have this part that is actually fitting together with another SLS part, but the entire piece itself can go and attach to other traditionally manufactured parts. It's really weird to see like a SLS part right next to all these traditional manufactured parts, and it's going to perform. It's going to be able to be used, and you're not going to be worried about, oh man, I printed this, so is this going to break tomorrow? These are end use parts.
Yeah, absolutely. And it's so fun. I love when I get a customer call and they're like, hey, Greg, this went through 1.1 million iterations already. I'm like, what? What is the cycle? Like, we have someone who's using it for automatic door opening and closing mechanism, and he's like, over 1 million cycles so far, no problems. We had someone call and he's like, been 2 years in my car, under the hood of my car as part of my exhaust fan, or what is it called? Not afterburner, but anyways, like, like this, it's basically uses as a junction to different branded parts. And I'm like, first off, wow, second off, cool, like it's just there in the engine and working. So here's some considerations though, and this is probably the number one thing that I'll see that is wow, the SLS is great, let's build this part, let's build this part, and then wait a second, what happened here? Long, broad, flat parts in SLS tend to have some warp to them. And that happens not when it's printing, but as it's cooling. When I melt material, it is melted in expanded state. As it cools, it starts to contract a little bit, and there's stresses that are built in as it's cooling down. In SLS, I'm building my parts from bottom to the top, and the top may be 25, 30 hours later. So if I have a long, broad part and I'm building it, in a vertical orientation or even some in a horizontal orientation, which is for another reason, as that part's cooling down here a little bit, it doesn't even exist at the top, and you get some really interesting stresses that start to occur in the design. So as that part fully cools while it's after the build, it actually may get a twist or a warp or a curl. The way that you work through this is a lot of times you design around it. Sometimes it's working with a glass fill or an infill material that helps stabilize it, and sometimes it's just may not be the right process for those type of longer parts, especially if it's like a big lid like FDM. It literally bolts the part down to the table when you're building it. Very good for those type of processes. The other thing is this is a powder bed. There's no emptiness in it. It is either a part or powder. So when I'm building parts and say I build a balloon and I have no exit to it, I actually just built a bowling ball that'll shatter and be full of powder. It's like a surprise balloon at the end and also be very heavy. And you need to consider how I'm going to get any excess material out of my part. So if I do have like a large area, I don't want to make it fully solid. And maybe I could, and I don't want to make it a hollow. Maybe I want to build a lattice or build it into a tube shape or build ribs into that. So this is going to be very quick. We have entire webinars on how to design for 3D printing, as well as a great guide here. But I do want to say that some of these things that are very common in designing for injection molding are great guidelines to start with when you're designing for SLS. The cool thing is then you could add the extra option of also you don't need to think about how to get a slide or a tool in there. You can now also build little features to accommodate off-angle holes or other features and go to town with this. Some of the more fun design for 3D printing options that I see in SLS designs are features like exit holes. This part here has a boss, usually using like a plastite or thread forming screw for it, with a blind boss feature, so essentially a blind hole. When I'm cleaning that out, it's very difficult for me to remove powder because I'm shooting a glass bead at it, but it's just filling up the hole and there's nowhere else for it to go. By designing in a perpendicular hole at the base of that boss, I could actually go shoot in the material and it has a place to force the other material out and fully clean out the part. The other thing to note is on this is like when you have confined, like if I have a confined hollow, so something where you do want to make it large and hollow, usually having 2 holes on it at least is helpful. So again, like a hole where I'm going to blast my beads in to clean up the material, another hole where it can exit out. You're going to have a much more efficient clean of that part. And you're not going to be surprised by like a patch of powder coming out 2 years later when it gets bumped the wrong way. The other thing, and I know Kevin, like we've talked about this a lot, you just love the phrase complexity is free. So tell me why is complexity free here?
Yeah, so traditional manufacturing, you have a block, and each sort of feature or added thing that you're bringing to this part, you have to actually cut away, and it takes additional time, additional steps, and it's much more difficult. For SLS and really any additive process, it's great that you're able to just design it and it prints regardless. So if you have a real thick, bulky part and you're like, I don't really need it that way, I want it to be lighter weight, but traditionally, I'm not going to go in and try and make a bunch of holes to lighten it up. For SLS, you can create a lattice in it and you can reduce a lot of the weight from that, and it doesn't really affect your price. Actually, as long as you're able to get material in and out, it might actually decrease your price, which
Yeah.
is one of those weird things involving
Volume
SLS.
and height. Volume and height are the biggest drivers. So like if you're making a brick, SLS is not the way for, the thing for you. But if you're making if you're looking to make something like a mold prototype or something where you have hollows or using the advantage of lattice or topology optimizations, it's fantastic because it is such a forgiving technology when it comes to design. I actually saw a note on what is a thin wall. And when I talk about that, I am talking about usually 0.5 millimeter is a thin wall, and the longer it gets, make it thicker. There's also a thick wall to that point. You really don't need to ever go over 4 millimeters wall thickness. In fact, like that even is kind of like overkill with a lot of SLS designs out there. Like you want to add rigidity and strength through ribs and other features versus just adding thickness to the part there. When I talk about 0.5 millimeter, I also mean that if you have a feature that's 0.4 millimeters or 0.3 millimeters, it's still going to be 0.5 millimeter because the laser power and the beam diameter are a certain size. So if you have 0.7, 0.6, 0.5, 0.4, 0.3 millimeter walls vertical, you're going to have 0.7, 0.6, 0.5, 0.5, 0.5 millimeter walls on the outcome. I know I have some questions coming in here, so I'm going to run through some of these. Just let you know, you don't just always get white or beige parts or carbon gray parts out of this. You can do some great finishes and we have a lot of these available through Xometry. Bead blasting is that standard matte. Shot peen will take shot peen and media tumbling will take that sugar cube, kind of bring it more to an eggshell finish. So shot peen is like a bead blast with ceramic media versus a glass media. Media tumbling is like more of a ceramic media that you're putting into a vibratory tumbler. We dye parts all the time. Media tumble dye black is actually the most common finish that we have for SLS parts, but we also do reds, blues, greens, yellows with that. Hand finishing, custom finishing is something you can do. Just understand that SLS material is really durable. So if I'm trying to hand finish that to a polish, it actually is a lot of manual work. You can cheat, add some sandable epoxy, fill in some of those nooks, and then sand it off, but it's manually moved. I'm really excited about things like vapor polish. So this picture here is a vapor polish then dyed black part. And vapor polish actually uses a chemical and kind of racks these into a closed cell system where a chemical will actually degenerate the outer surface of the part and then re-solidify it, evening out those bumps and crannies, and you get some really amazing parts.
Yeah, I really love this, and it's not just a aesthetic thing. It will seal that surface, so if you have fluids running around your parts, this is a great way to make sure that that's not actually leaching in. And I think it's a great finish if you're like, man, I love all of these options for design flexibility and what a great material, but it still looks like a printed part. Vapor polishing is a great way to be like, it looks now like any old injection molded part.
Yeah, and these newer technologies they really are amazing. Again, a lot of us have been working with this technology for 15, 20 plus years, and you really haven't seen anything like it. So I'm excited about what's coming out there and what's available, because the chemical resistance of nylon has always been a restrictor of, can I vapor polish it? ABS, acetone, sure, but nylon's like acetone. I take a bath in that. That's fine. It doesn't react. I'm gonna run past this sum up because we got I see some amazing questions coming in here, but the very quick summary here is elongation. Nylon 11, this thing could stretch, it could bend, it could really, it's extremely durable, it could take an impact, bump out. When I look at glass fill, aluminum fill, mineral fill materials, I'm adding that fill to add purpose to the design. I'm adding it for rigidity. I'm adding it for high heat deflection. You know, in the case of aluminum, sometimes I'm adding it because it's just cosmetically awesome to look at and handle. Carbon fill. This is a logarithmic scale. That little bump out between that and the HST is actually a giant number. This is over double the stiffness of the other materials. It is just an extremely stiff, high performance material, and it's one of the more premium ones you'll see. Like if you look at our pricing on it, but it's you're buying on purpose. You're not just like accidentally buying it. It's like it is, you know, it just adds so much application to your design and your design intent. Nylon 12, again, Nylon 12, Nylon 11, we talk about this commodities. Nylon 12 still is kind of the king. It's the most commonly ordered. You tend to have the quickest lead times, you know, great parts out of it, and usually, you know, the lowest cost. Although, like, these are, you know, very similar because they're all bulk-based processes. So again, I see questions. Keep them coming. If we don't answer them in the next 10 minutes, I'll go a little over so we can address as much as we can. I'll also I'll get some answers out to you afterwards as well. So you can find us online. Go to Xometry.com. You can go and select different 3D printing processes, compare them, take a look at pricing and lead time, as well as select these new materials that we have. So the materials that Xometry has, as well as with our partnership with Stratasys Direct Manufacturing. All we require is a 3D CAD file, and you'll get instant pricing. You can change your quantities, and the price will update. You could even add features like tabs and inserts and finishes directly online to get instant pricing that way as well. I also recommend at Xometry.com/resources. We have design guides for all our processes, including selective laser sintering, that are much more comprehensive than that one slide I gave you. A really great capabilities page that's kind of a directory, so you can find our design guides, our resources, etc. there. And if you're just looking to learn about additive, I highly recommend the complete guide to 3D printing, other resources. It's called the Ultimate Guide, and it's a novel. You know, get your reading glasses ready, but it has a little bit of everything in the subject matter. Also, with Xometry, we have a great referral program. Xometry.com/refer will give you a referral code. So if you know someone that may be interested, you could send them your code. If they create an account, they'll have $50 of credits that they could use against their first purchase. If they purchase, you get $50 of credits too. So you know, share with your friends, pay for your prototyping. And let's go to Q&A. So I'm not sure, Luce and Kevin, do you see the Q&A? If not, I will MC this.
I am
I
not
cannot.
seeing it.
All right.
Yeah.
Okay. All right. I have the power here. So actually, I saw a lot of questions about water absorption. And this is a little bit of a different thing. Nylon does have water absorption to it. There are materials like polypropylene that are more moisture resistant. I will say this is why Xometry and even Stratasys Direct Manufacturing, we offer so many different processes. Polypropylene was just actually launched for HP multi-jet fusion under our instant quoting engine. That has a low moisture absorption. So if there is interest in that type of application where you're submerging parts, actually under MJF there's polypropylene. There are polypropylene variants for SLS as well. It's not on our direct drop-downs right now though.
Yeah, and I would definitely say if you're looking at secondary processes like finishing or dyeing or anything like that, is just to account for some of that moisture absorption. Particularly for painting, make sure that you sand and seal that surface. If you apply too much paint, it can potentially cause issues with warp or something like that, depending on how thin the walls are.
Yeah, and I've used epoxy to seal very often in my lifetime. So
works perfectly.
Epoxy is fantastic. It will discolor a little bit, but it does the sealing for you.
Yep.
So I have I think this is interesting. So Kevin, Lewis, if you guys want to chat on this, where do you see topology optimization and generative design come in when it comes to additive manufacturing through SLS? Like, do you see that often, or what are you typically seeing?
Yeah, I'll let Kevin kick this off, and then I'll.
Yeah, so we're starting to see it a lot more. This is still a part where people are learning how to use this, and where generative design lives in topology optimization for things like, we say, oh yeah, just add a lattice, but there's a lot more that goes into it, and how do you design that correctly? And we're still trying to, learn that as an industry. So it's becoming more common, but I would say, not anywhere near every part has some sort of topology or generative design.
Yeah, I would say it's definitely customer specific, if you will, and their level of familiarity with something like that. We still see a lot of things come through with traditional, molding designs, which is fine. SLS can do that. But there is definitely a bit of a knowledge gap in terms of, how you can best leverage SLS. We published a industry-wide survey just last year, and that was one of the top things identified by OEMs and respondents was that knowledge gap, learning exactly how to design for SLS, how to leverage it to the best of its ability. And that's why I'm excited to get to talk a little bit about that today.
Yeah, and I was going to say, sometimes it's access to software. Topology optimization, generative software is at best an add-on. Usually it's when you want to do something, even adding textures to parts, which I feel should be a click and go experience, is, watching 3 hours of YouTube instructionals and going through like 3 different formats to add like a mat to a part. What's exciting is that is all accelerating. It's all accelerating right now. So it should be part of just standard CAD. And you can see a lot of CADs catching up with some sort of 3D print module. It's mostly focused on desktop versus with these industrial processes that we run more commonly, but it's all catching up. So that's what's exciting. I had a question too about metal composites, and I know sometimes SLS is confused with like DMLS or DMLM, but and I could touch on this a little bit, but a lot of that has to do with thermal control. So like, why can't I use this process directly to print metals? The biggest thing is, have you ever tried to take a piece of aluminum foil and have it stay completely flat on a table? It'll always curl up on you. It'll always kind of buckle up. When we're printing on these very small layer by layer bases, I have a recoater, like a blade going through, and if I have even a little bump up, it grabs it and drags it apart. And this happens in SLS too sometimes. If you're doing like a really broad sinter, sometimes it gets cool on the edge, curls up, and you have a build fail. Metals like that times 100. Like that's why with metal sintering, you're actually sintering down to a build plate. So it's more similar to like stereolithography in that manner, where it actually has structures, mechanical structures, desperately holding that part down as it's being fused together layer by layer by layer and building the bottom to the top. So you're not able to do free floating parts in direct metal printing processes. I'll give some caveats there, but for the most part, that's true. With SLS, everything's thermally controlled. That allows us to do those little nuanced laser touches to create something from a powder to a solid base, and then keep that stage there. So in SLS, it's like almost like if I take a golf ball, stick it in flour, and let go, the part's not sinking, it's not floating, it's just there in space. And that has to do a lot with thermal processing. There's heaters and sensors everywhere in these machines. They really are very sophisticated pieces of industrial equipment.
Yeah, the big difference to me is what's actually doing the work for the most on these processes. SLS, those overhead heaters are bringing that powder right below its melting temperature, and the laser's job is just kind of trip it over into melting. Versus DMLS, all the work is done by the laser essentially. We're not, bringing some metal up to its melting point and just using a laser. It's a much more powerful laser, so that's a big difference.
There's been some pretty great advancements over the last couple of years. I think of the Velo Sapphire system with the metals aspect, where they can build some parts free floating within the powder. It's like the ultimate marriage of hardware and software. And those two things really have to work in concert with one another to achieve something like that within metals. It's certainly a little bit more realistic in terms of wide applicability for plastic at this point.
Yeah, and the Velo program, again, I could talk all day. It does need a beard. It needs a starting point that vectors out to build itself. So it almost has a root feature to make it so it can build without supports. So you can't. It's not a high mix design either. There's still intent behind each design there. There's actually a good question. So a lot of these questions are between multi-jet fusion and selective laser sintering. What are the differences? Do they use the same material? Hey, it turns out we have a powder, well, I guess if you're looking this way or maybe up and down, but we have a powders expert here named Kevin. So if you want to talk about that, like what's, in a nutshell, what's the elevator pitch between MJF and SLS?
So they are very similar. They're using, for the most part, the same materials, these nylon bases. And the big difference is how are we doing the melting of that powder? So we still have the same idea where we have some overhead heaters that are bringing it up towards that melting temperature, but not actually tripping it over. So SLS, you're using a laser shining down and drawing your part. Where HP MJF, you have a print head that's going over top of that white powder, and you're jetting a carbon black doped ink. And then there's another IR heater that's going over top of that as well. And so that change in emissivity, that black part that you just jetted, it's going to absorb a lot more energy compared to the white powder that you did not jet anything on. And so one part melts, the powder stays the same, and you have a lot of the same ideas on, you are using no supports, you're using overhead heaters, a lot of the same materials. So they are very similar. That big difference is how are we actually melting those parts.
Yeah, and in some of these materials may be chemically the same, like the nylon 12 versus nylon 12. They do have their own unique brands to them. The glass fill nylon is a different glass fill nylon that we're going to throw into, our SLS machines, for example. And just again, I live in a world of broken parts because I break these. So I break these for demonstrations. And this is also my prop for watch Will It Tumble, one of our latest videos. But this is a SLS nylon part. The white powder is fused with a laser and it comes out white. In this case, this is actually polypropylene, but again, it's more of an off-white powder. But you can see it's gray, and actually MJF parts in general are going to be this gray color because of what Kevin mentioned. So you actually are inking the part, and you can see polypropylene didn't survive as long as SLS did, but you're inking that part, and then you're fusing on top of it. And there is a kind of a detail compound that is kind of that bridge between the black and the white material, the base material. So you almost have a gray exterior. If I took a knife and cut into this, or took a bandsaw and cut this in half, MJF parts will actually be jet black on the inside, even color MJF, fun enough. Where obviously SLS is going to be just the base material color because of the way that the heat infusion occurs is different. So let me see. I'm going to cover one more question, I think, and then I'll catch up at the end here. So, this is a good one, and I can answer this a little bit, but I'll also let you guys. So we talk about a lot of times. Shock and vibe and heat tests, so like that -40 to 140 Celsius. This question is specifically on that -40, or it's -40 Celsius or Fahrenheit, they're the same. How any material tested in those lowest temperatures? Do you have any experiences with that?
I've done tensile testing with the carbon fiber filled material down to -15 degrees C. And I did not see any significant drops in mechanical properties, which was an interesting find. I was expecting it to be much more brittle when we got down to those cold temperatures, but it actually survived really well, and there was no distinguishable difference.
Yep, I've done that. I've tested, so I've taken parts, and where I used to work, we had a thermal chamber where you could do the full heat differential tests. Well, that -40 to 140 usually has to do with like air. -40 is usually like air cargo shipping, so it's not like I'm using it at that temperature. They do survive that temperature. They can take those. So those materials tend to take those swings. Higher heat deflection materials tend to be more stable, especially if you're looking to use them at a higher working temperature. But if you are looking to, put this on a, make an SLS part, put it on a C-130 on air conditioned through Antarctica, and expect it to arrive in a box and survive, yeah, it probably will. It actually will. It's very, very impressive material. So I have on here too, we have a great promotion code, and I first should have said that a little earlier, 3D Print 25 for $25 off your next Xometry SLS order. We want you to give it a try if you haven't. So that's for any of our SLS offerings, and again, 3D Print 25. We'll also give an email out with that information as well. But Louis, Kevin, this is awesome. Like I am so grateful to have you on board for today's webinar. We're really excited about bringing on a powerhouse like Stratasys Direct Manufacturing as a partner for manufacturing on Xometry's marketplace. Any final words?
Just thank you. We thoroughly enjoyed it. You got 3 SLS geeks together, and so we love talking about it. I hope that everyone here learned what they needed to about these, and hopefully, certainly, give it a try. These are incredible materials. I think that we've done a great job of demonstrating that today, and it'll be great for your next project.
Yeah, just thank you so much to everyone. And it was really fun. I hope we do this more often.
Yeah.
Thanks so much, and thank you all so much for attending. I really appreciate it, and have a great day.
Awesome. Thank you all.
Bye, everyone.